Okay, let's continue. So, my next goal is what can be called Newton-Leibniz theorem. In L1. So, what is Newton-Leibniz theorem, or can be the basic theorem of calculus? Is the following: f in C of R. So consider a continuous function, and consider the function f of x equal integral, say, from f0 to x, f small of t dt. So it is the integral with variable upper bound. And the theorem is the following. Then df dx equals f small of x. So derivative of integral with variable upper limit with respect to this upper limit is equal to the value of function at this point. So it is really shows that differentiation and integration are mutually inverse operations. And now, what happens if f small is just function in L1, so a measurable function? Suppose f in L1 of R. Then we can also define f(x) equals integral, no, let us integral of minus infinity to x f d lambda. Yeah. So we no, because the function L1, so this integral makes sense. The integral converges. And the result theorem is the following: df dx equals limit f capital x plus t minus f capital of x divided by t when t goes to 0. Let me write, goes to 0 from above. Yeah. And this limit exists for almost all x in R, yeah, and is equal to f small of x. So this is the theorem, a very good theorem proved by Lebesgue and then improved by different authors. So it is the best generalization of this theorem of Newton-Leibniz to this context. No, before I go to the proof of this theorem, I wanted to show one spectacular application of this theorem. Application is the following. Um, Consider the function f equals a characteristic function of some measurable set A of x. A is a Lebesgue measurable function, Lebesgue measurable set. So it is again Borel set union with possibly set of external measure 0. So it is in Lebesgue sigma algebra, and sorry, it is A. And then what is this? For almost all x, we have the following thing. First of all, f of x plus t minus f of x divided by t, what it is equals integral from minus infinity to x plus t chi a of s chi a d lambda minus integral from minus infinity to x chi a d lambda divided by t equals integral from x to x plus t, yeah, chi a d lambda divided by t. But what is this? It is nothing but Lebesgue measure of the following set of A intersection with x plus t divided by t. Yeah. And what is this? And by this theorem, for almost all x, this is equal to chi a of x. Yeah, for almost all x. If it is equal, so if equal, it is a. 1 x in A, 0 x not in A. Yeah? So let me draw a picture. We have some set, no, I don't know, it can be exotic set, hard to even to describe. Maybe it is impossible to describe it in any good reason. We know only that it is element of Borel algebra or Lebesgue sigma algebra. and we take a point x plus t, and you see that for almost all x, one or other thing happens. Either this limit, we take the mass or measure of this set A from x to x plus t divided by t. It is a sort of density of this set. Yeah, it is definitely between 0 and 1. And then it is a mean density from x to x plus t. If you take the measure of the set here and divide by t, we have the mean density. No, simply if the measure is the mass, we take the mass divided by the length. It is so linear density, mean density. And then you take a limit. Where is the limit? Here is the limit. When t goes to 0, and it's just local density at this point. Yeah. So if you take smaller and smaller distance between x and x plus t, then consider what happens here. And it turns out that only two possibilities are with probability or with measure 1. Either it is the set of density 1 here. Yes, so almost all is filled by this set near the point x, or it is density 0. So maybe just some sporadic points from A gets here, but mostly, I mean, everywhere but at the set of measure 0, this happens. So either the density is 1 or the density is 0. This means that if you take t positive but small, then the mean density here will be close to 1. Yes, close to maximum, or close to 0, close to minimum. But nothing in between. This is a really important theorem. It holds in a wide variety of situations. Here is one particular situation, the density on the line. It can be density in domain of higher dimensions. The same, we will discuss it when we consider the higher dimensional Lebesgue measure very soon. And it is a very useful theorem. Why I say that it is very useful? Because I use it in my own work. I think it's enough. In my research, I find this theorem really useful and use it more than once. As we can express it in the following way, that the set cannot have a density 1/2, for example. Yeah. This means, let me say, we can find maybe for some sets some points where really this limit is equal to 1/2. So the set has density 1/2 at this point. Yeah, maybe I will ask you to produce this example. But for almost all points, for almost all x, the set, Lebesgue measurable set, has density either 1 or 0. Yeah. So it is a very important thing. But all this will be validated if we prove this theorem. this theorem. So now I'm going to prove, and this proof is far from easy. It is not transcendentally uh, difficult, but it is not quite elementary and requires some new devices. So let me start from the first. It is Markov's inequality. Markov's inequality. It is the following thing. Suppose we have function f of x more equal than 0. Yes, f in L1 of R. So consider a measurable function in L1, integrable function. It is not fx. Then the following is true. X in x, and we have x as mu, the usual triple measure space. And the theorem is the following. Measure of the set x in x such that module f of x more than c less or equal 1 over c norm f in L1. Yeah. So the set where the function is very large necessarily has small measure. No, it is easy to prove. So f1 equal integral module f d mu. Yeah, it is this integral over all x. And let me denote this set A with index c, where the function, modular function, is more than c. It is more or equal integral over AC module f d mu. Yeah. No, it is negative, non-negative function. We restricted integration to some subset. Now, on this set AC, module f is more than c. Yeah, so it is more or equal. So the coarse estimate of this integral is the following. We take, say, infimum of this function times the measure of AC. So if the function is more than c, that integral is more than c times measure of AC. C times measure of AC. Yeah. No, if you return here, go this norm F1 more or equal C times measure of AC. So measure of AC is less or equal than 1 over c norm f in L1. Yeah. No, small but lovely theorem, and it has a lot of application. First of all, in the probability theory, and not only. Here it will have really great applications. Next, I will consider another classical thing. It is the next component of the proof. It is Vitali covering theorem. Vitali covering theorem. We have already met this name. This is the author of example of non-measurable set. Yeah. So definitely this man has a great imagination. So this is also a very beautiful imaginative thing. So what is Vitali covering theorem? No, first of all, one simple notion. Triple segment. What is a triple segment? Suppose we have a segment on the line, this segment I. Yeah. Now triple segment is the following. We add to the segment two segments of the same length on the left and on the right. On the right and on the left. Yeah. And altogether is denoted by 3 times I. Yeah. So it is tripled segment. And now the lemma. Suppose we have a finite number of segments. No, 5 segments on R. Without any further hypothesis. Simply we take they can overlap, that can be disjoint, simply arbitrary n segments. Then we can find a subset of segments. Let us denote I, say K1, I K2, and so on, I Km. Now m less than n, such that first I Ki, I Kj is so these segments do not overlap on one hand, and on the other hand, I1 union of initial segments union is fully contained in uh, triple I K1 union and so on, union tripled IKM. Yeah. So we can find among these segments uh, a smaller number of segments which do not overlap themselves, but if they tripled, they already cover all of them. Yeah, and we will see very soon why it is important, why it may be important. It is really interesting. Now let us start proof of it. It is a beautiful, beautiful lemma. So it is proved in the following way. First of all, let us put these segments in the decreasing order of length. Suppose that the length of A1 is more equal than length of I2, and so on. And the shortest is the segment IN. Now, if they are in different order, we simply rearrange, number them so that we can always have this situation. And now, now define. IK1 is simply I1. So we take the longest as the first. We started from this. IK2 is the first in this line, in this order, segment which does not intersect with IK1. Yeah. So maybe we take the first longest, next maybe still overlaps with it, and if you take one after other and reach the first segment which does not overlap with I1, we call it IK2. IK3 is the first segment which does not intersect with IK2, and so on. If we cannot find this, we reach the end of this, and we at the some step we cannot find the next one. All the which are after this IKM are intersecting with some of the previous ones, then we stop. And now the claim is the segments IK1, IK2, IKM have the required property. required property is this. That if you take instead of each of these segments, this is the tripled segment, yeah, then this system of tripled segment will cover all the segments here completely, yeah. No, why? Why? Uh, Let us see. In fact, suppose that the segment ij, sum of the segment, uh, uh, is not in the list ik1, ikm. Yeah. So we did not pick it. Did not include. Why can we? Why didn't we include it? It is because we choose several segments by this rule, and the ij is has not a non-zero intersection with one of previously chosen segments. Yeah. If it had no intersection, if it has no intersection, then we will choose it. But if we did not choose it, this means that it has in some intersection non-zero, at least at the endpoints, with one of the previously chosen segments. Then there is exists a segment, say IKP, chosen at an earlier step, such that ij has non-zero intersection with IKP. Is not intersection is non-empty. So we have the picture. This is our ij, and this is the previously chosen segment. This segment IKP at the step number P. And they have this non-zero intersection, yeah? But we arranged our segments in decreasing order of length, yes? So the length of ij less or equal than length of IKP. Yeah. So, and IKP is longer. This means that if you add here another segment, just attach it to this end of IKP and go add the segment of length equal to length of IKP, then this part of ij, which is beyond IKP, this part, is shorter than this segment IKP, so it will be covered. And this is covered because IJ has this intersection with IKP. And it cannot say cover all the IKP because it is shorter. Yes? No, if it is from the closer to the right, then this half works. If we have this configuration, then we have also this part of triple. So this is the triple IKP, yeah, triple IKP. It is all this. Yes, and you see that in both situations, is it from the left or from the right or in the middle, this is IJ will be completely covered by tripled IKP. Yes, here is explanation why tripled. Yeah, so hence IJ is covered by triple IKP. No, okay, so we see that every segment which is in this list is already the middle third of triple the same segment, and every segment which is not in this list will be covered by tripled one of the previous chosen segments. Yeah. No, okay, I can wave hands a little more, but I think it is convincing. So this means that this lemma works. Again, this lemma is a popular tool in different problems of real analysis. And here is the first instance which we meet, where we meet this lemma. Now the next is another new object, which is called Hardy-Littlewood maximal function. Hardy-Littlewood maximal function. Notice the following thing. Suppose we have a function f of x in R, f L measurable. So we have a Lebesgue measurable function. I don't say even that this function is integrable, so it is in L1, just Lebesgue measurable. And consider the following new function. Consider the function f star of x. We do it the following. Integral from x x minus t to x plus t module f d lambda. No, we have to divide 1 over 2t, and we have to write supremum over all t more than 0. Yeah. So it is the function f star of x. It is, so to say, no, majorant of this function. No, for example, if you have a function which is 0 here and 1 here, yeah, it is 0 for x negative and 1 for x positive. So what is its maximal function? No, if you take this point, no, let us b, yeah, and find integral from b minus t to b plus t f d lambda. So what it is? No, for and 1 over 2t over the 1 over length. If t is less than b, in this case, then it is mean value of the function from b minus t to b plus t. If t is small, then this mean value is 1, because the function is 1 here. Yes, if t is larger, then it will be less than 1, because this integral is less than 2 t. It is here is piece which is 0. And if t is goes to infinity, then we have no, the following thing. B is here, it is b plus t, b minus t, and asymptotically, when t goes to infinity, half of this segment will, on the half of this segment we have 1, on other half we have 0, no, up to relatively very small piece here. And so the mean value goes to 1/2. Yeah, so if you follow this definition, then f of b equals 1/2 for any b. Yeah. Now, if our function is, say, characteristic function of segment 0, 1, so here it is 0, here it is 0, and here it is 1. Then we have a different situation. Here, for short one no, I'm sorry. Here the function will be 1 here, of course, because it's supremum. So for small t, the value of this is 1. If b is positive, yeah. No, for larger it is less than 1. So supremum is 1. So this maximal function here, it is 1. And here, this function is for small t, it is 0. But then it grows and goes to 1/2. So this function, maximal function, here is 0, here is 1, here is 1/2. Here also this maximal function is 1 here. At this point, the maximal function is 1/2. Yes, because integral will be divided by the length is exactly 1/2. And if you go further, then this function will decrease and go to 0. And here it decreases and goes to 0. No, in fact, it is not quite interesting. No, interesting is what happens if, say, the function is not bounded. Yeah, if it is unbounded, so grows. Yeah, then this maximal function can become infinite at every point. Yeah. No, it is mm, maybe not very interesting thing to study different cases. But now I want to consider Hardy-Littlewood inequality. No, inequality for this Hardy-Littlewood function. So consider let us take point C, and we are interested in the set where this function is more than C. Suppose f in L1 of R. Now it is already in L1. Define B, C is the set of B in R such that F star of B more than C. And the theorem is the following, that the external measure of BC equals less or equal 3 divided by C length of H in A1. It is quite interesting. Instead of in the Markov inequality here was 1 over C and here 3 over C. What happens? Yes, so we took some transformation. No, you know, just imagine you have some function and the maximal function says something about no average behavior of this function near some point. Yes, and for this function you can, I think we can imagine that here this function will be large, and here will be small, and here will maybe go to 0. Yes, so the function is it gives some rough description of no I don't know. In fact, it may be tricky object, this maximal function. So we have to use it carefully. Let us go to proof. So BC is the set of point such that f star of b more or less equivalent c. The first thing is the following. BC is open. It's an open set. It is already very good. So why it is open? So we see f star of x is defined as supremum. If we have supremum more than c, then for some t, this is more than t. Proof. If say b in b capital C, then supremum over t 1 over 2t integral from x minus t to x plus t module f d lambda more than c. If supremum more than c, then for some t, this integral also will be more than c. Yeah. Then for some t, 1 over 2t integral x minus t, x plus t, b minus t, b plus t, not x but b. Module f d lambda more than c. Yes, and now the next is that, but integral, say, from x0 to x module f d lambda, this integral is continuous as a function of x. It is continuous. Why it is continuous? We had previously a theorem by the previously proved theorem. If f in L1, then integral over some set, let me A, module f d lambda less than some function omega of A, module A of a measure of A, where omega of S goes to 0, as S goes to 0. So we had the following result, that integral of modules of function, integrable function, uh, over some small sets of small measure uh, is bounded by some function of the measure, so it goes to zero if the um, measure of the set goes to zero. Yes, non uniformly over all measures or all such sets. No, simply if you uh, consider this function, it is the graph of a function, yeah, and how we defined the Lebesgue integral, we divided the y-axis into these segments, yes, and we consider the product of, say, value of this number, the height of the, I would say, this floor. It is a floor, it is ceiling here. We take the floor in this beam times the measure of the set, projection of this on the x-axis, yeah? Take these integral sums, and we simply disregarded what happens here above this. And if you continue this process, then we will have some limit. Yes, finite limit. This definition of integrability. And if you consider a set of small measure here, yeah, we can consider the set of the same measure such that it includes this peak, and the integral will be larger because the function will be larger. But even in this case, integral here will be bounded and go to zero if this threshold goes to infinity. This is why we have this result, but the function omega of s, it goes to zero, but can do it quite slowly because integral converges, but it can converge slowly. So the measure here can be very small, a measure of if you take the set where this function is large. This measure can be small, but the integral is still large. It is finite, but still large. Now consider the function x to the y equal x to the power 1 minus 1 plus epsilon, yeah? Y equals x to the power minus 1 plus epsilon. And the integral and on the segment 0, 1. Yes, then this integral of this function converges if epsilon positive. But if epsilon goes to 0, it converges slower and slower. And for epsilon equals 0, it diverges. So near this divergence, we can have that this rate of tendency to 0 of the function omega of s becomes slower and slower. But anyway, it is conversion, and this means that if you consider integral from x0 to x, integral from x0 from x to x plus t, yeah, uh, minus integral of f0 to x, which is equals integral from x to x plus t. Yeah, this function. This is a function of t. Yes, this integral goes to 0 when t goes to 0, because the measure of this domain of integration from x to x plus t goes to 0. And this means that the function, the value of this, no, I would say indefinite, definite integral from x plus t to x, this difference goes to 0. So this means that this function integral as a function of the upper limit is continuous. And so if you consider this 1 over 2t integral b minus t to b plus t. And I consider uh, 1 over 2t integral from b minus b plus say tau minus t b plus tau plus t. So I shifted this integral by tau, small tau, and because this is continuous function of tau, and for tau equals 0, it is more than c. F d lambda is a continuous function of tau, which is 0 at tau equals 0. And if at tau equals 0 it was more than c, then for some small, maybe small range of tau, it is also more than c. So this means that together with the point b, the points b plus minus tau also are in the set b capital C. So this set is open. Oh, my God. So the BC is open set. Now, if it is open set, then yeah, BC is open. So it is BC is a union of open intervals. Very good. And now we take closed segments which are inside each of these open intervals, such that they feel no, okay. So consider closed subset F, F capital, in BC. Yeah. No, for example, in each of these, or in some of these open intervals, we take smaller closed interval. Yeah. Uh, uh, will show that uh, the size of f less or equal than 3 over c norm f 1. And this is enough because we can take this uh, set arbitrarily close to the set BC itself. Yeah. So no, we consider just these closed intervals. Whew. Okay, so we can assume that f equals I1, I2, In. So, okay, so on each of these at the point, if B in F, yes, consider the point B in F, then its neighborhood is also in F. There exists T depending on B such that uh, B minus T, B plus T uh, no, it means that such that 1 over 2t integral from b minus t to b plus t uh, f star d lambda more than c. Oh, now uh, so what does it mean? For any b, sum of such interval from b minus t to b plus t covers this point b. So this means that f equals union of b minus t of b, b plus t of b, yeah, t of b. union B in F. So F is covered by no continuum of these segments. So by the Heine-Borel lemma, or what is Heine-Borel lemma? That if a bounded and closed set is covered by any set of open intervals, then it is possible to extract a finite number of intervals which still cover this set. There exists a finite family of intervals I k equals by d minus dk minus t of dk plus t of dk, no, k1 and capital, covering F. So F is covered by this number of, by a finite number of these intervals. Now we can estimate the size of this F. Of F, norm F. And here will be one or two tricks, maybe three. F is a subset of I1 union of IN. Let it be N. Again. So F less or equal I1 union IN. Again, yeah? Now, the length of union of intervals is not more than sum of lengths. So it is less or equal length of I1 plus length of I2 plus length of IN. Now we can use the Vitali theorem. Yes? By the Vitali theorem, no, I missed the term. Union of these segments is covered by union of tripled segments. 3 times ik1 union 3 ik2 union 3 ikm. Yeah. Yeah, so this is covered by these tripled segments. And this is less or equal than length of 3 times ik1 plus length of 3 times ik2 plus and so on plus length of 3 times ikm. Yeah. No, length of 3 tripled segment is 3 times length of the segment. So it is equal 3 times length of ik1 plus length ik2 plus and so on plus length ikm. And these segments are non-overlapping, like these segments. Segments no, these intervals, they have zero intersections with one another. Yes. So now we can estimate the length of each of them by integration. So let me write ik1 it is a sum of initial segments. So what is ik1? It is ik1. It is from bk1 minus t of bk1, bk1 plus t of bk1. Yeah. So this is the this segment, and over this segment we have the following. Why we chose this segment? What is interesting about this segment? It is that 1/2 t of bk1 integral over ik1 modul f d lambda is more than c. Yeah. Yeah, it is how we chose for any point B. We found this B was small, was a point in the set B capital. So we there exists a neighborhood from B minus T to B plus T, depending on T, it depends on B, such that the mean value of the function module f is more than c, yeah, uh, and uh, let me write 1 over module ik1, yeah, this, and so this means that module ik1 equal is less or equal 1 over c times integral over ik1 module f d lambda. Yes, I move it here and c is here. And so now if I substitute here, we have length of f less or equal 3 times ik1 1 over c integral ik1 module f d lambda. It is this plus 1 over c integral over ik2 module f d lambda. It is this plus and so on plus 1 over c integral ikm module f d lambda. Yeah. No, here 1 over c, I put it here. Okay. It is equal to 3 over c, 3 from here over c, integral. So I have to take the sum of this integral. So over ik1 union ik2 union and so on union ikm. It is a domain of integration module f d lambda. And at last it is less or equal. Here this is non-negative function. We integrate it over the union of non-overlapping segments. And now we can estimate if you integrate over the whole line. It is less than 3 over c integral over the whole r module f d lambda, which is equal 3 over c norm f 1. Whew. So once again, f was a closed set, any closed set measurable, which is which is a subset of BC, of the set where this function, maximal function f star, is more than C. Yeah. So we know that this BC equals union of say AI BI, yes, or non-overlapping. It is because it is open set on the line, it is union of interval, countable union of intervals. Yeah. So we can take, say, some closed segment inside the first interval, the second interval, yeah, and so on. No, we take finite number of intervals so that the measure of the rest is small, less than epsilon. Yes, and for the measure of this, we found the estimated measure of this union of these closed intervals is less or equal than this. It is constant and doesn't depend on which number of intervals. So this means that the measure of the whole set, open set, is also less than intervals. And so less than this number. Again, so let me write BC is the set of B such that F star of B more than C. Yes, it is the definition. And we have the following estimate, that the outer measure of BC is less or equal than 3 over C norm F C. So it is some connection between the properties of F star, the maximal set function, and the function F itself. It's L1 norm. Okay, at last we finished the proof of this theorem, and let me finish this part, and next time all this will play to prove the theorem about, I would say, how to call it, no, I want to call it Newton-Leibniz theorem for or I call Newton-Leibniz-Lebesgue theorem. But Lebesgue invented so many theorems, I think it's the only theorem which can be called Newton-Leibniz-Lebesgue. Okay, so let's finish at this note and continue soon with the next issue. Have a good time. Bye.